Hello everyone, hope everyone is fine and doing good. So what is update? Well, update is this is gonna be the fourth video on kinematics video lecture series. In my last video I talked about speed and velocity. Now what I'm going to do in this video, I'm just going to talk about velocity and acceleration. So to maintain the continuity, let's get started. Now first of all, take a look on velocity. As we already know that velocity is a vector quantity. So it means for its complete description we required two parameters. The first one is magnitude and the second one is direction of motion. And we also called magnitude as speed, right? Now at this moment I am interested in how many ways the velocity of a moving object can change. So being a vector quantity, velocity can change in three different ways. Number one is when there is only change in speed. So we can say speed changes only with no change in direction. And in this case we will study about the one-dimensional motion. Case number two is speed constant. But direction continuously changes. In this case we will study about uniform circular motion. And the case number three, when both the parameters change, both speed and direction change. And in this case we will study about non-uniform circular motion. Okay, so in later videos we will be discussing each and every case in detail, but in this video I am just focusing on the case number one, when the speed changes but direction of motion doesn't change. So let's see how. Now let's take a look on two different situations and we'll try to see what is going on here. So the first case is, suppose any object is moving from A to B, and let's divide the total time into equal parts. This is 1 second, 2, 3, 4, and it is 5th second, and it is given the position of this object at different instant of time. It is 2 meter, it is 4, 6, 8, and it is 10 meter. Okay, so this is the first situation. Now let's see the another situation over here. This is the object which is starting from its starts its journey from point A and it goes to point B. This is 1 second, 2, 3, 4, and it is 5th. Here it is given the position of this object is 2, this is 18, and it is 32, it is 50, and it is 72 meter. Okay, now first let's discuss about it, and after completing it we will discuss this condition. Okay, so here what I want to do first, I want to calculate the average velocity. So for this I will use x2 minus x1 upon t2 minus t1. What is this x2 minus x1? This is the change in position of the object between two instant of time. Okay, and I can write down this as delta x over delta t. Now let's take the different values of t1 and t2. Suppose if I take t2 equal to this 5th second, then I can say v averages comes out to be, so if I take t2 equal to 5 and t1 equal to this t equal to 0, so this is 5 minus 0 and it is 10 minus 0, so it will give me value 2 meter per second. Okay, so this is the average value. So the average value is what? The average of all the values of the velocities which the object might have taken between points A and B. But if you notice here, we have information of position of the object at a different instant of time. So we can apply this formula for all those instant of time which are in between points A and B. So let's do it now. Let's suppose this time I take t2 equal to 4 and t1 equal to, let's assume it is 2. So I can say this comes out to be, again it comes out to be 2 meter per second, right? So let's take another values of t1 and t2. This time I'm taking this is t2, 3 is t2 and 2 is t1, and it will give me, yeah, I'm getting the same value. This is 2 meter per second, right? So in this case the object is moving with constant speed, right? Now I'm interested in calculating the value of speed exactly at this moment. Basically I want to find out the velocity at time t equal to 3 seconds. Okay, so for this what should I need to do? I need to choose the value of t1 and t2 so that delta t is going to be nearly equal to 0. Let me explain what I mean. Suppose I take t1 equal to 3 and t2 equal to 3.000 many times 0 and it is 1. So if I take the difference of these two instants, then delta t comes out to be this. So this is nearly equal to 0, right? Now if I select the value of t1 and t2 such that this delta t is going to almost equal to 0, then this notation changes into this form. So what is the change? Let's write down it here. We replace this delta x by delta t by this sign. Okay, so what is this dt? This is a very small time interval, and this dx is what? Change in position corresponding to dt. Okay, so basically this dx and this dt are very small quantities, right? And this is something we call what? Derivative of x with respect to time t. Okay, so technically it is written as like this: d bracket inside x and it is dt, where this x can be a polynomial function, it can be a trigonometric function, it can be logarithmic function, and it can be exponential function. Okay, and we will explore all of these functions when we will be discussing the questions from quizzes. Okay, so that is for latter part, but now here just focus on this dx by dt. Right, now do you notice that when I write down the formula of the average velocity, this is delta x by delta t. Now if I make this delta c so small that it changes into dx by dt, now what about this average velocity? Now it's become instantaneous velocity. Okay, so this is the extremely important point. Okay, now let's see how we can find out the derivative of a polynomial function. Okay, so let's see it. Take x is any polynomial function k t power n plus c. Well, I can expect that you are all already familiar with the concept of polynomial function. You might have studied in earlier classes. So let's take on this. So how I can find out the derivative of this? Since x depends on time t, so I can write down this as dx over dt, and I can write down this as k d over dt. This is inside bracket t power n plus dc by dt. This is going to be 0, right? Because this is just a constant. It is not going to change with respect to the time t. So this is equal to 0. Now let's focus on this. What is this? So I can write down this further, dx upon dt, k times, this is n t power n minus 1. So basically what I have done, I have just take the power of t and put in the coefficient place, and then I reduce the power of this t by factor 1. Okay, so this is n minus 1. So this is what the derivative of any polynomial function. Okay, now let's try to apply this in this particular situation. So for this I should know what is the relation between the position of this object with respect to the different instant of time. Now if we look it very carefully, then you can notice for every next second the position is going to be twice of that particular time. Okay, for example, if you take time t equal to 1, position is 2 meter. If time t equal to 2, position is 4 meter. So that is twice of 2, right? So this is twice of 3. So in that sense I can say position x is equal to 2t. So this is the polynomial function of position of the object in terms of time t, right? Now if I apply the concept of derivative over this function, first let's write down it here, x is equal to 2t, and if I do the dx over dt, it will give me 2 into 1 t 1 minus 1, and it will give me 2 t power 0, and dx over dt is what? This is 2. And what is this dx over dt? This is the instantaneous velocity, right? Because I have already mentioned over here, right? So this is what 2 meter per second. Okay. Now the question is, at which moment the velocity has this much value? Now you can notice I have just reduced this delta t so small that I have just obtained this value, right? Basically I have taken the derivative of this. So whatever be the instant of time between a and b, the instantaneous velocity is going to be same, and that is intuitive, right? Because we have seen so many time interval and we have found the average velocity comes out to be the same. So for any particular instant of time, the instantaneous velocity comes out to be the same, right? So this is about this particular case. Now let's focus on this case, what is going on here. Now here in this case, I just want to start with the same way as I have started in this. So here first calculate average speed, or you can say the average velocity. It is what? V average is equal to x2 minus x1 upon t2 minus t1. So here let's assume x2 is this point, so it is 50, and x1 is this point, so it is 0, and it is 5 minus 0. So it will give me the value 10 meter per second. Now let's take some other values. Consider this is t2 and this is t1, so it is 5 minus 4, and here it is 50 minus 32, so I am getting here 18 meter per second. Now let's take one more value. V average is equal to, this time let's take it is this is t2 and this is as t1. So it is how much? 3 minus 1, 18 minus 2, so it comes out to be what? It is 16 upon 2, and I will be getting 8 meter per second. So here what we have noticed, for a different time interval I am getting the different average velocities. So what does it mean? That simply means that the object is traveling with different speed at different instant of time. Now as we already have done the derivative concept, so let's apply this concept over here, but for this we need the information about the position in terms of time t. So if we look it very carefully, then we can say that the position of this object satisfy this relation, and we can check it out. If you put the value time t equal to 1, then it is going to be position 2, and if you put the value time t equal to 2, so this is 2 to 4 to 8, and if you plug in the value time t equal to 3, so this is 339 into 2, that is 18. So this relation satisfying this condition, right? So now I want to apply the derivative concept on this. Okay, so if I do this, x equal to 2t square, then I will be getting dx over dt is equal to 2 into 2t 2 minus 1. So I am getting 4t, right? So this is what dx over dt equal to 4t. And what is this dx by dt? This is the instantaneous velocity, right? Now the question is, at which instant this is going to be the instantaneous velocity? Well, in this equation you can notice instantaneous velocity depends on time, because here is a time parameter, right? So whatever be the instant you want to calculate the instantaneous velocity, you can use this relation. So let's assume if I want to find out instantaneous velocity at time t equal to 2 seconds, so it will give me v equal to 4 into 2, so I will be getting 8 meter per second, right? Similarly, if I take another instant of time, let's say I just want to find out at time t equal to 1, so it comes out to be 4 meter per second, and here let's take time t equal to 3, so it will give me 12 meter per second. Similarly, time t equal to 4, it will give me value v equal to 4 into 4, that is 16 meter per second, right? And at time t equal to 5 seconds, it will give me 20 meter per second, right? So let's figure out all these values over here. So this is time t equal to 0, and this is the initial velocity. Let's take the velocity at this point, it is 0, and here it is 1, 2, 3, 4, 5. What is the velocity at this point? This is 4 meter per second, right? And at 2 it is 8, it is 12, 16 and 20 meter per second. So this is the information which we have obtained by using the concept of derivative, right? Initially what we have given this situation, and by using the concept of derivative we could find out what is going on at a different instant of time in terms of velocity, right? So this is the information we have just extracted by using the concept of derivative. Okay, so let's try to understand what is going to be the next. So here we have obtained the different speeds at different instant of time by using the concept of derivative. Now what I just want to do here, I just want to find out in 5 seconds how much the change in speed take place. So let's do it now. In 5 seconds change in speed, that is equal to 20 minus 0, it is 20 meter per second. And if I want to find out the change per second, change in speed per second, so I will use concept of direct proportion, and I can say it is 20 meter per second upon 5, it will give me 4 meter per second square, right? So what is this value? This is nothing but this is the average acceleration, right? So what is the formula of the average acceleration? So let's write down it here. So average acceleration is equal to change in speed. So let's write down it as delta v upon delta t. Delta t is what? This is the change in time. Okay. So this is the formula of average acceleration. How it can be? Basically, if you notice here, what I have done, I have just divided the change in velocity, or you can say the change in speed, by the change in time. Okay. So based on this, I can say this is the formula. Okay. Now what is this? This is the average acceleration. Okay. Here let's talk about this value 4 meter per second square. So this is the average acceleration. What does it mean? This is the average of all the values of acceleration that the object might have taken between A and B. Okay. Now I just want to verify here in this particular case, the instantaneous acceleration means acceleration at any particular instant of time, that is going to be the same. Okay. Now I have the tool of derivative, so let's apply the concept of derivative to verify it. Here, as we know that average acceleration is delta v over delta t. Now if I want to find out the instantaneous acceleration, then I can use the concept of derivative. Okay, so for this what do I need to do? I need to make this delta t smaller and smaller so that it is almost going to be equal to 0, right? So for this what I can do, I can write down this as A instantaneous is equal to dv by dt, right? So I have written down this expression directly by using the concept of derivative, right? Okay, so now what is this v? So let me write down like this. What is this v? This is the expression of velocity, right? And I can find out this expression from here. Okay, so this dx by dt is nothing but the expression of velocity in terms of time t. Okay, so let's plug in this value over here. So basically I can write down this as d over dt, and this v is dx over dt. So if I write down like this, then it becomes d2x over dt square. So what is this? This is something we call what? Second order derivative of x with respect to time t. Okay, so what is the second order derivative of x with respect to time t? It is what? It is instantaneous acceleration. Okay, so now let's use the expression v equal to 40 over here and try to find out what it is. Okay, so here I can say this is d over dt and it is 4t, and if I do the derivative of this 4t with respect to time t, I will be getting 4 meter per second square. So that is the same thing which I have already got here. Okay, so in that sense we can say instantaneous acceleration is going to be same, that is equal to the average acceleration, and it is only when the acceleration of the moving object is constant. Okay, so what does it mean by the constant acceleration? In the next every second the speed or the velocity is going to be changed by the same amount. Okay, so this is about the constant acceleration. Now I just want to discuss the geometrical interpretation of derivative, so let's do it now. Now to understand the geometrical meaning of a derivative, first try to plot the graph of x equal to 2t square. So let's plot the graph over here. Let's assume it is t equal to 1, it is 2, 3, 4, 5 and it is 6. So corresponding to time t equal to 1, position is 2, corresponding to time t equal to 2, it is 8, corresponding to 3, it is 18, corresponding to 4, it is 32, next is 50 and it is 72. Okay, so let's plot all these points. So we can say these are the points. Let's join all of these. And it is going to be a curve. Okay. Now what I want to do, I just want to find out the ratio corresponding to the different time interval. What is the ratio? Ratio of difference of the position of the object corresponding to different time interval. Okay. So let's take here t2 equal to 6, t1 equal to 3. So corresponding position is 72 minus 18. So it will give me how much? It will give me 54 upon 3. So this is 18 meter per second. What is this? This is the V average. V average corresponding to this time interval. Okay. So let's take this point is time t equal to 6. This is time t equal to 3. So let's join these 2 points. Okay. So this line joining from t equal to 3 to t equal to 6 represent this V average. Okay. Now let's make this time interval little bit smaller. Okay. So for this I am taking time t2 equal to 5, t1 equal to 3, and it will be give me 50 minus 18. So this is 32.2. So this value is 16 meter per second. Now let's take this point time t equal to 5 and this is time t equal to 3. So let's join these 2 points. So this line joining from time t equal to 3 to time t equal to 5 represents this V average. Similarly, if I take t2 equal to 4, t1 equal to 3, then it is 32 minus 18. It is how much? It is 14 meter per second, right? Now the line joining from time t equal to 3 to time t equal to 4, it represents this V average. Now what I want to do next, I just want to make this delta t so small that delta t is almost going to be 0. Now if I do this, what will happen to this line? So you can notice here, as I decreasing the time interval, this line getting shorter and shorter and getting shifted downward, right? So for this instant, when I do the time interval so small that this delta t is going to be almost 0, then I can write down this as dt, and the corresponding change in position is represented by dx, right? So this dx over dt is nothing but the v instantaneous, right? So for this condition, I will obtain a line which is tangent to this point. Okay, so this is nothing but this tangent to the curve, it represents the instantaneous velocity. Okay, so the point is derivative of x with respect to t is the tangent to the curve at a point. Okay, now we also called this tangent as a slope. Okay, so this is also called what? This is also called a slope. So we can write down here slope of a curve. Here I am taking xt curve. Okay, so let's mention over here slope of a curve at a point is called derivative of x with respect to time t. Okay, and it gives us instantaneous velocity. Okay, so basically this is valid for xt curve. Okay, because we have done analysis for this xt curve. So this is the slope, this is the slope, or we can say the tangent to this curve at this particular point, and the tangent at this point gives you the value of instantaneous velocity. Okay, so this is about the geometrical meaning of derivative. Now let's see some question based on the discussion which we have done so far. Now let's say this question: assume the position of any object is represented by this position vector. Let's assume it is 5t square I cap plus 2j cap. The first part of this question is, what is velocity at time t equal to 5 seconds? B part is, what is average velocity for time t equal to 5 seconds? And the third question is, what is average acceleration? Okay, now let's add one more part to this. Check whether magnitude of instantaneous acceleration is equal to magnitude of average acceleration. Okay, so now let's solve each and every part one by one. So let's write down this equation once again. R equal to 5t square I cap plus 2j. Now as we already know that the coefficient of unit vectors I and j gives the position of an object along x and y axis. So let's separate them. X equal to 5t square, y equal to 2. Now let's take the derivative of x and y. This is dx over dt, which is velocity along x. It is equal to tan t, and this dy by dt equal to 0, right? Okay, now based on this vx and vy, I can construct the velocity vector, which is vx I cap plus vy j cap. So it comes out to be tan t I cap. Okay, so this is the velocity vector. If I want to find out the velocity at any particular instant of time t, then I can put that value over here. it will give me the velocity vector at that particular instant of time. Now here I just want to find out the velocity at time t equal to 5 seconds. So let's plug in this value over here. So it will give me 50I, and the magnitude of this velocity is 50 meter per second. Okay, so this is the solution of question number 1. Now let's see what is this question number 2. So for V average is nothing but the displacement upon time, right? And the displacement can be written in terms of position vector r5 minus r0, and it is 5 minus 0, right? What is this r5? Position of this object at time t equal to 5, and position of this object at time t equal to 0, which is r0. So let's plug in the value of time t equal to 5 in this. So it will give me 125 I cap plus 2j minus 2j, right? And here in the denominator it is 5 minus 0, so I will be getting 25 I cap. This is the average velocity vector. Now what is the magnitude of this? Magnitude of this is simply 25 meter per second. Okay, so this is the solution of question number 2. Now let's see what is this question number 3. What is the average acceleration? Average acceleration is written as change in velocity upon change in time, right? And what is the change in velocity? Change in velocity is v5 minus v0 divided by 5 minus 0, right? So what is this v5? Let's put this value time t equal to 5 in this. So it will give me 50I, and it is 0, v0 is 0, here it is 5, so it will give me 10I. Okay, so this is the average velocity vector. What is the magnitude of this? Magnitude of this is simply 10 meter per second square. Okay, so this is the value of average acceleration. Now let's see what is this part, part number 4. Here in this case we need to check whether instantaneous acceleration is equal to average acceleration or not. So for this I would be needed the derivative of this velocity vector. So let's do it here. As we know, velocity is 10t I cap. If I take the derivative of this, dv by dt equal to 10 meter per second square, right? So this is nothing but a instantaneous, and here we can see average acceleration is equal to the instantaneous acceleration, and if it happens then the object is said to be moving under constant acceleration. Okay, so this is the solution of this question, basically the solution of all the subparts of this question. Now it is the time of quiz number 3. Question number 1 of quiz number 3 is, suppose the position of any object is represented by this position vector 2t square I cap plus 5j cap. The question is, first part is what is distance and displacement at time t equal to 5 seconds. B part is what is velocity at time t equal to 5 seconds. Third part is what is average velocity for t equal to 5 seconds, and the last part is what is average acceleration. Okay, so this is the question number 1. Now the question number 2 is, suppose the position of an object moving along x-axis is represented by x equal to 2t square plus 5. The first part is what is distance and displacement at time t equal to 10 second, and the B part is what is velocity and speed at time t equal to 10 second. And the next question is what is average acceleration. Now the third part of quiz number 3 is, let's assume x equal to 2t square minus 10. The first part is what is distance and displacement of object at time t equal to 10 second. B part is what is speed and velocity at time t equal to 10 second. Third part is what is average velocity for time t equal to 10 second, and the last part is what is average acceleration. So these are questions for quiz number 3. So that's all for today. We have discussed so many things in this video. So see you soon in the next video. Until then, keep watching and stay connected for further updates.